Agora foi. Aí tem que chegar o sinal aqui primeiro. Okay, we are on. Welcome, everybody. It's a great pleasure to have with me Dr. Aviad Albert. Sorry for my French pronunciation. Aviad Albert is a postdoctoral researcher at the University of Cologne, Germany, where he works on phonetics and phonology with emphasis on speech prosody. He is interested in auditory perception and linguistic cognition, and he is, like myself, fascinated by the tension between dynamic and symbolic models of language. Thank you so much, Aviad. The floor is with you.
Thank you so much. All right, so hi everyone. Thanks very, very much for watching this. It's a great honor for me to present my work in this forum. My name is Aviad Albert, as you know, and I'm currently working as a postdoc researcher, as you also know, in the Collaborative Research Center Prominence in Language in the University of Cologne, where I also received my PhD at the phonetics department. All right, so to set the stage, my approach is biased towards auditory perception and cognition, and I'm interested in studying how sound is perceived in general, and specifically how sound is processed as linguistic information. So to start, I'd like to actually present you with a small demonstration of auditory perception. My apologies to anybody who already seen this before, because I showed it quite regularly nowadays, but I think it's quite helpful to understand what I'm trying to explain later on. So I'd like to start this with a demonstration of what is known as band-limited impulse trains, or BLIT. And BLITs are repetitive sequences of very transient impulses that can be useful, for example, in digital sound processing, if you want to generate different oscillator waveforms, for example. That's not what I do with it. I generate BLIT synthesis on my computer, where I just control the amplitude and rate of the impulse train, essentially to drive a visualization system that helps us see and hear what I will try to highlight here today. So first of all, these things sound like this. So hopefully you all heard these clicks.
Okay.
Right, that's important. Okay, so the main point behind this demonstration is to highlight the so-called regimes of auditory perception, as we call them, and hopefully that will be very clear in a second. What you see now are visual representations of two BLITs at two different rates, and I will walk you through this very briefly. So first of all, those white panels that you see at the bottom, they show the time domain representation of the clicks within a 1 second window, right? So you can see, for example, there are 4 clicks here in 1 second, which correspond to the rate being 4 hertz, right? So the number of vertical lines shows the number of clicks per second. And trust me, I counted, these are 120 clicks for the 120 hertz. Now, the 2 dark panels above are FFT representations. They show the same signal in the frequency domain. And in all of them, frequency is plotted on the x-axis from left to right, both here and here. In the middle panels, power is plotted on the y-axis, reflecting amplitude of different frequency bands. And what I want you to note is that this is a still image of a moment frozen in time, which captures the graph here on the left panel when it is high. But in real time, I want you to realize that this is visibly going up and down, right? Because these are this. This is not the case for this panel here, which is visibly stable. All right, the top panels here are spectrograms, where power is depicted with color and time is plotted on the y-axis, and here it's moving from bottom to top in the plot, right? So here it's important to know that this is kind of different from most people are used to the typical orientation of spectrograms as in Pratt, where time moves from left to right. But here, in order to keep everything aligned on the x-axis with the same frequency, time is moving from bottom to top. It's not really important. It's just to make sure that this is clear when I now show you these two different effects. So the set of 3 panels on the left side, they demonstrate a rhythmic effect at 4 Hertz. You already heard it. I'll play it again. The important thing about the experience of hearing this is that there's a clear perception of rhythmically related isolated clicks, which appear here as this straight power graph in the middle panel. As I said, it's going up and down to represent that. And as corresponding transient bursts over time, which appear here as these horizontal lines on the spectrogram, right? So they keep adding up. So here we have actually 2.5 seconds, and this is 4 Hertz. So if you will count, you will see we have 10 equally spaced clicks on the spectrogram here. Now, the set of 3 panels on the right side, they demonstrate a periodic pattern at 120 Hertz. The only thing that really changed is that the rate of these clicks just moved up from 4 Hertz to 120 Hertz, so 120 clicks per second. Now, this repetition is too fast for the perception of isolated events with a rhythmic relationship. So instead, the perception of a continuous signal takes over. And this one sounds like, I will play it now, but please be careful because this one is a little harsh. So if those speakers are very high, then be careful. Okay, it's not very nice because these are impulses. They are very transient. But if you think of the voicing from the vocal tracts, these are also click trains, right? So the way we produce vocalic sounds is also with the click train. Although our pulses, each pulse is a heavier click, and it has this whole filter of the vocal tract, which we don't have here. So this is why this is so harsh. But actually, this is a harmonic sound, and not only it's harmonic, the rate of repetition is now reflected in the fundamental frequency of the resulting structure. So you can see that in the successive bumps on the power graph in the middle panel and in the corresponding vertical lines now in the spectrogram at the top. So I think what is kind of cool is that the spectrograms very neatly reflect these 2 distinct auditory regimes in perception. The horizontal lines in the left for temporal regime and vertical lines in the case of the spectral regime. And sorry again for this noise. Now, the change between these 2 regimes does not happen at once. We don't move from one effect to the other effect in one magical moment. There seems to be a transitional range between the 2 effective regimes, which, as you can see and hear, is less decisive between the 2 states. So at 24 Hertz, the blit sounds like this. I hope you heard that. And repetitions within this transitional range can still be perceived as successive isolated events. I hope you heard that. Although they are a bit too fast for effective rhythmic perception. It's very hard to tell if they move faster or not, or if they're isochronous or not. They're just too fast for that, and definitely for training our motor system to that. At the same time, they already exhibit some trademarks of a continuous harmonic sound. We can even see that here, although that is also mostly indeterminate, right? So we have these 2 effects, but they're both kind of weak. And again, very neatly, the spectrogram in this case shows both faint vertical and horizontal lines to represent very nicely what we also hear, I think. So hopefully, if your intuition is similar to mine, what these FFT representations do nicely, especially these spectrograms, is kind of separate these 2 effects in perception. All right. So what I hope I managed to highlight in this demonstration is our ability, the ability of our auditory system to integrate events within specific timescales within with 2 distinct effects. So this is the basis of the framework which I call priors, which stands for perceptual regimes of repetitive sound. And the idea in priors is to reduce auditory perception into 2 distinct regimes, this temporal regime and the spectral regime. And the idea also is that these two perceptual regimes, they do not overlap. So maybe some eyebrows already are lifted and say, okay, well, that's simply the frequency and time domains. It's not a new thing. And I agree, it's very similar to the notion of frequency and time domains, but these are two mathematical representations of the same thing. And the idea of calling these perceptual regimes is to highlight the fact that they are alive in two different environments. They do not live in the same environment. They are active within two separate and distinct timescales. And each one of them highlights two major effects in auditory perception, which is the perception of dynamic rhythmic patterns at the slower timescale, and the perception of periodic signals at the faster timescale. And in essence, these are the two main types of temporal integration that we can achieve with sound. We do not perceive rhythmic relationships below 0.5 hertz for events that are separated by more than 2 seconds. So there's a vast literature. The exact numbers here, by the way, and the numbers I will show you in this slide and the following ones, don't take them as too strict. These are just like marking the ballparks of these things. Essentially, the main effects are in the center of these ranges, not at the boundaries. So if we can roughly say that between 0.5 hertz to 12 hertz, we have that window of temporal integration, which I call here the temporal regime. Likewise, we hardly perceive pitch differences much above even 4,000 hertz, but let's call it 5,000 hertz. Let's be generous for events that repeat more than 5,000 times per second. Now, most of you probably know we are considered to be sensitive to frequencies much higher than that, up to 20,000 hertz, more realistically 16,000 hertz. But our ability to resolve fundamental frequencies really deteriorates severely after 4,000 hertz. So really our ability to perceive pitch is pretty much within a smaller range than the range within which we perceive frequencies in general. Now, I want you to know that I'm using the terms rhythmic and periodic to denote two distinct effects, although there's no universal convention for this distinction. So some researchers will use these terms interchangeably. I'm trying to be consistent internally to my story, but please be aware that this is not consistent with the rest of the world, sadly. All right, so by focusing on these two major effects in auditory perception, priors can be useful for linguistic models, which is hopefully why we're here. Specifically, I think priors can do a lot of heavy lifting in explaining why syllables evolve to be the way they are from perceptual perspectives. And syllable size, according to this view, is optimized for exploiting our ability to perceive slow versus fast distinctions within the time scale of the temporal regime. Right? So the idea that things move slower or faster, and our ability to have a mental representation and perceive that, that's something that syllable size kind of exploits nicely. Oops, sorry. Well, syllabic content, that is the segmental makeup of syllables, is optimized for exploiting the ability to perceive the differences between high and low pitch distinctions. So syllables, according to this view, I said that syllable size eventually average at approximately 5 hertz. So usually every 200 milliseconds, that would be the central tendency of syllables universally. And that's pretty much, again, at the center of that temporal regime, nicely optimized for delivering rhythmic effects. And syllabic content, that is the segmental material of the syllabic nucleus, is optimized for delivering pitch between roughly 50 and 800 hertz. So this is the how we kind of go back into linguistic models from this very general auditory framework. Now, in the low frequency timescale of the temporal regime, speech rate is the main effect, and in the high frequency timescale, I argue for a link between periodicity and the segmental makeup of syllables. So in other words, I argue for a link between sonority and the spectral regime. Now, let me just elaborate a bit before moving on. By speech rate, I actually mean dynamic speech rate, which stands for a broad range of phenomena such as phrase edge lengthening and pauses, which play an important role in chunking speech and in handling turn taking, etc. So I will get back to this topic at the end of this talk. I will not say a lot about everything I just mentioned, but I will go back to this idea of speech rate in the lower, slower time scale, lower frequencies. But I should also note something about the sonority, about the higher time scale. Although I focus on sonority and prosody, in the spectral regime, we could also detect aperiodic noise, which is characteristic of fricatives, and transiency, which is characteristics of plosives. So there's also lots of segmental phonology that we could cover with this view, although I will not do it here. The following part of the presentation will focus more closely on sonority and prosody at the spectral regime. All right. So in 2022, I published with Bruno Nissenboim a study in cognitive science that presents a novel model of sonority, proposing both a phonetic basis and a novel dynamic principle of syllabic well-formedness. And we presented data from perception experiments that essentially lend support to our proposals. Now, I will spare you the details at this stage. It's pretty rich, and most of it is not going to be relevant for us. So I will just very, very briefly show you now this slide where you can see the fits between the predictions of different competing sonority models in our study, which are depicted as these blue violins in each panel. And the actual response time results, which are overlaid in the red dots. Okay, so you can see here our proposal called NAP at the bottom left, and the 4 variants of SSP that we tested against it at the top 2 rows, and the null model that we also ran for the sake of this comparison. And again, for today's presentation, I will not go into too many details from that study, although I'll be happy to elaborate later if anybody wants. What I do want to highlight is the proposal that was part of this whole story, which we put forward for the phonetic basis of sonority. Now, phonetic basis of sonority has always been a source of many views. There's no clear consensus behind it. So it's a kind of like muddy waters to step in. But we have a good reason to do that, I think. So in line with the Prior's framework, we hypothesize that syllables likely evolved to exploit the spectral regime as pitch-bearing units, as explained earlier. And so sonority, if you think about it this way, is very likely the active trace of this evolutionary drive to carry pitch information in the nuclei of syllables. So this kind of boils down to 2 related hypotheses, actually. So the first one is that sonority is causally linked with our ability to perceive pitch, that is, pitch intelligibility. And the second derived hypothesis is that the proper acoustic correlate of sonority is the periodic energy in the acoustic signal. I'll say a few things about it a bit later. So essentially, I claim that syllables were optimized to be pitch-bearing units since speech has communicative roles in all language systems, where syllables carry the pitch information, either a lexical tone or intonational tune. And as I think we all know, our auditory system is specialized for pitch detection. So we have many good reasons to make these assumptions. Now, please note that this is not entirely new. Previous accounts listed here, and there are others, but these would be probably the prominent ones, suggested that sonority may be related to periodic energy or pitch in so many words. So yeah, this should be said. Now, sonority, I think, is a very interesting meeting point between segmental phonology, where we may be interested in phonotactics, that is, predicting possible segmental sequences, and prosody, where we may be interested in representing pitch contours, weight distinctions, and speech rate effects. If sonority is indeed tightly related to pitch intelligibility, as I claim, then we should expect to find its acoustic exponent, periodic energy, playing a crucial role in prosody and intonation. To that end, we developed a toolbox called Proper, which stands for prosodic analysis with periodic energy. And that kind of evolved on the side from the main project that I had for my dissertation, which was to model sonority in terms of pitch intelligibility, and eventually kind of like honing in on this idea of periodic energy. And then we realized we could do other things with it. And when I say we, I mean a group of people. So the Proper toolbox has been developed by a team of researchers from Cologne in recent years. And it's an open source collection of Pratt and R scripts that are available in an OSF project. And I urge you all to scan this QR code and check it out. So I will try to briefly explain what we do with Proper. I'll use a speech example to illustrate it. Let me first play it.
Can I ask you a question?
You heard? Okay.
Yeah.
So that's a sample from a study in which we extracted the expression, "Can I ask you a question?" from the TV News Archive. And yeah, it's an example I like to use. Now, what we see here is the standard waveform and F0 representation above. And now F0 is either present or absent along the time axis. Hence, we call it a binary representation. Right? So whenever you have a voiceless portions, then you have discontinuities in the trajectory of F0. That's normal. Now, we extract the periodic energy curve from the acoustic signal, as I briefly mentioned. I didn't explain anything about it. So periodic energy is similar to the amplitude envelope or the intensity curve of the pitch-inducing components in the signal. Probably didn't say much either. So we can think of it as the quantity dimension of pitch perception. So maybe one way to think about it is F0 gives you the quality of perceived pitch, but not the quantity. Right? So if you have two tones of 100 hertz, it doesn't get you to 200 hertz. What quantity of pitch perception is, according to this view, modeled by periodic energy. Now, also, before I move on, I wanted to be super clear. So this here is our periodic energy curve. The one you see now is the one that we produce using Pratt with those codes that I mentioned earlier. But what I want you to see is that it basically follows, like a regular intensity curve, the waveform you see below, right? So it's like the amplitude envelope of this waveform. That's not incredibly different. But what I want you to notice is those two portions where we have stretches of voiceless elements. So we have ask and we have question, right? So you see those discontinuities here. In terms of periodic energy, because these are aperiodic and voiceless fricatives, we go all the way down to zero, both here and here. Now, note, this is not without energy. So the intensity curve differs from the periodic energy curve exactly in these portions where it's not vocalic or not vocalic enough, and then we will see this gradual decrease in the underlying level of the pitch perception. All right, so what do we actually do? The first thing we do is this: we take this interaction of the two curves, the quality and the quantity of pitch perception, to yield what we call the periogram. And that's an enriched visual representation of the pitch contour. So periograms are like spectrograms in the sense that they represent acoustic power as a third dimension in the plot. The F0 curve, and notice that now it has it's thicker in some parts and darker in those parts. So it's darker and wider where the corresponding periodic energy is higher, right? So in those peaks, you can see also it's wide. And vice versa, of course, it's going to be diminish as we move down here. So underlyingly, we have an interpolated F0 curve in this case, and it's modulated by the corresponding periodic energy to provide this periogram for us. Okay. No, that's just a visualization of individual tokens, which I think is useful. But we also use proper to measure and quantify large sets of speech data, aggregated data. And so the proper metrics are always confined to syllabic intervals. And so the first task before we can measure anything is to obtain valid syllabic intervals. And that in and of itself is pretty interesting. So we use the periodic energy curve to locate syllabic boundaries, right? So most people use the amplitude envelope, often of a band-filtered audio signal, to achieve something very similar to that. We don't need to do that because actually we have a very similar to a band-limited audio signal that we take the envelope of, and we don't kind of arbitrarily just or not arbitrarily limit the different bands. We actually take the periodic components, which again is very similar to, for example, take a low pass filter on high frequencies, which would usually give you most of the noisy elements in the speech sound. So that's pretty standard. We use this energy, the fluctuations of the periodic energy curve, to locate syllabic boundaries. And we employ this algorithm that uses gradually smooth derivatives to locate minima along the periodic energy curve, which is a pretty cool process. Now here, these would be the peaks along the thick purple curve, right? So every time you see a peak, you see also these red vertical lines. These are the automatically detected boundaries. Now, these procedures can be adjusted to also take text grid boundaries into account. And in this example, you can see the text grid boundaries are depicted in the dotted black vertical lines, while the red lines, as I mentioned earlier, they show the automatically detected syllabic boundaries. And what's really nice about this algorithm is that we can tell it to use the text grid boundaries either to force the automatic detection there, but more likely and more useful is to just be informed. So as an example, you see that there's also a peak on the purple curve here, which would have resulted in a boundary on the nasal coda where we don't want it. But it knows not to put the boundary here simply because it's too far away from any boundary that's on the text grid. So it uses the text grid boundaries to inform it rather than to force the location of boundaries, which is a really nice solution. All right, so now once we have the proper demarcation of syllabic intervals, we can run the ensuing measurements. So we can measure the weight or the heaviness of syllabic intervals in terms of the area under the periodic energy curve. So the periodic energy mass, or what we just call mass. And now the dashed red lines in the center of each interval represent the center of mass. It is the average time weighted by the periodic energy, effectively dividing each syllable into two equal halves. The center of mass provides an important syllabic landmark for all the following metrics. But I want to, before we move on, to say a few things and show a few things related to mass. So two important things to note is that with mass, we explicitly assume that perceived quantities have both duration and power. So it's the area under the curve. We're summing this region. We're not averaging, which is what people often do, or definitely not looking at the peak for that matter. We assume that the quantity of the syllabic weight is captured with both duration and power, because in reality, these two entities, these two subcomponents do not exist. So we never perceive duration without power and vice versa. Of course, we say that we still think it's very interesting to look at duration and power separately. It's not that we're throwing them out of the window. It's just that from a perception perspective, they do not exist on their own. And the second thing is that we calculate weight as a local relationship. So the area under the curve of each syllabic interval is compared to other areas within the same intonation unit. So these values here that you see are actually how strong each syllable is with respect to other syllables in that same utterance, same unit. So it's always a very, very local relationship, which allows us to immediately, if we throw these numbers into, if we aggregate data and throw these numbers into a descriptive statistics model, we will see signals if they're strong before we need to do any more sophisticated analysis. So that's pretty nice. I want to show you a few examples of studies that use mass. So a 2022 publication by Simon Rössig, Bodo Winter, and Doris Mücke compared a large set of phonetic markers in their ability to detect the presence versus absence of a focus accent in German intonation. And they found that mass was the most robust measure, right below F0 min, which should be considered complementary. So that's a very nice result. And crucially, I wanted to notice how mass here also outperforms both RMS amplitude, which is a bit like the average intensity, and vowel duration, which together can be roughly described as those two subcomponents of mass. A 2021 study on Maltese intonation led by Maria Yayu, we investigated whether certain high tones that appear on word initial weak syllables also cue prominence. So here we compare aggregated values of the unstressed word initial syllable that has a high tonal event. And these are the left violins in each panel, the red ones. We compare them to the stressed syllable in the same structures, and these are the violins on the right. Each panel here. Now, as you can see, these two panels on the right, they show us the separate measurements for duration. That's the one here, and intensity. That's the one at the bottom, and they give us conflicting results. So if you measure duration, it seems to very clearly favor the stressed syllable. But if you look at intensity, it seems to favor the syllable that bears this high tone. And we really needed to look at mass to get a clearer answer with respect to the question that we're still pursuing with other means. But and I'm just showing you a very small portion of a bigger study. But the idea here is how we can use these things in effective ways. And I think that's another good example of mass being effective, especially when we have these conflicting results from the two subcomponents of what mass is. And we really have more and more evidence that it's probably not cueing prominence in this position. I also want to mention a 2021 study on the intonation of Italian learners of German that was led by Simona Zbrana, and she investigated patterns of deaccentuation based on information structure. And previous reports claim that the Italians do not deaccentuate the second item that if it's given, and that would be in this case the red violins in syllable 3. But let me take a step back and explain. So we're looking at a speech that was prepared such that we always have two words, adjective and noun. It's always disyllabic, and it's always penultimate stress structure. So we always have two syllables per word. Each time the first or the third syllables in these combinations are the stressed ones, as you can see here. And the differences in the context that was created for this experiment is that sometimes the first item is given and the second is new, and sometimes it's the opposite. The first is new and the second is given. So these are the color codes here. As I said, the previous reports claim that Italians do not deaccentuate the second item. You could see here a trace of that, but that's in the mass dimension. So usually that was said about F0. So while this may still hold for F0 patterns, we actually found that they do seem to deaccentuate, as you can see here, when they learn German. But it's in the mass rather than the F0 dimension, which was already an interesting finding. And even more interesting is that it doesn't seem to follow information structure. It's across the board. So also the green violin in syllable 3 here seems to be deaccentuated in mass. All right, so back to proper. We turn to measurements that involve the F0 contour based on interactions with the corresponding periodic energy time series now. And we use the centers of mass to characterize the F0 trajectory as a measure of the local pitch change from syllable to syllable. And we call this delta F0. So to calculate delta F0, we measure the difference between F0 values at consecutive centers of mass. All right, so we pick this at the center of mass, we take the F0 value, and then we very simply just look at the differences going syllable to syllable. We normalize this measurement by dividing the spectral distance with the overall F0 range of the speaker, and we can do other types of normalization. That one is not even the most state-of-the-art. Finally, for these proper metrics that I want to present, we also account for the trend of the F0 movement within syllabic intervals, right? So the delta F0 was from syllable to syllable. What is the difference in the current syllable compared to the previous one? But here we want to characterize also what is the shape or the general shape of F0 within each syllabic interval. And so to do that, we need to add another landmark that accounts for the shape of the F0 contour within each interval. And we call this landmark the center of gravity, as it is directly inspired by the tonal center of gravity by Barnes and his colleagues. I have the reference here. Okay, so what we do is that we measure in synchrony the distance between the center of periodic energy mass and the tonal center of gravity on the F0 contour at the same interval each time. We normalize this measurement by the duration of the containing syllable in percentage scale. Now, as you can see, when the blue center of gravity is to the left of the red center of mass, the main trend of F0 shape is falling. When the blue center of gravity is to the right of the red center of mass, the main trend of F0 shape is rising. And when the two centers are largely in sync, F0 is likely exhibiting a plateau. Now, synchrony is primarily proposed as an alternative to standard tonal alignment procedures. The main advantage that the synchrony metric provides concerns the fact that it does not require turning points on the F0 curve to serve as landmarks, and it does not require F0 to be continuous to allow comparisons. With synchrony, we can characterize the main trend of the F0 curve within every syllable of interest. And we introduced the synchrony metric in 2019 in a 2019 study led by Francesco Cangemi, where we demonstrated that the synchrony metric is as good as tonal alignment in separating questions and statements in Neapolitan Italian data. Again, the 2022 paper by Russisch, Winter, and Mücke that I mentioned earlier also compared a large set of phonetic markers in their ability to detect different types of focus marking in German intonation. The previous comparison was absent or presence of accent. Here it's different types of focus. So synchrony was found in this case to be at the top, right after peak alignment and tonal onglet, but also doing a very good job. And one final and very recent example that I want to share today is from a study led by Gustavo Silveira. And he will present this one in the forthcoming InterSpeech this summer. So I'm just going to show a tiny little bit from it. This study investigates intonation differences between two varieties of Brazilian Portuguese. And the periograms that you see here, they show two individual examples where we take the synchrony and delta F0 values from the pre-stressed, stressed, and post-stressed syllables in each one of those sentences that we took. So these are semi-spontaneous speech, very different sentences, but we just locate those same positional points. And in this case, we're looking at the declaratives with non-terminal intonation. Now, the aggregated data that we collected can show us the extent to which any differences are systematic. So I'm just showing you part of this larger study, but you can see here that this is captured most clearly in this case with values on the post-stressed final syllable, which is also summarized nicely in this abstract scheme. So you can see this is a very handy exploratory tool when we want to throw the kitchen sink at something, when we can compare, and then the signal can very nicely show up. Okay. So to conclude, the proper toolbox can cover aspects pertaining to prosodic weight and pitch contours with 3 different metrics. We have mass to cover prosodic weight. We have delta F0 to cover pitch differences between syllables. And we have synchrony to cover the main pitch trends within syllables. Now, before I wrap up, I want to briefly go back to the low frequency oscillation of the temporal regime, where we can rethink about rhythm in speech. And I'll do it a bit too briefly, but it's kind of important. I think it kind of helps maybe show a more complete picture. So in a new forthcoming book chapter, co-authored with Martin Grice, we claim that rhythm in speech is not the regular pattern of occurrences that we expect from isochronous signals, We claim that rhythm is the timescale within which we are capable of temporally integrating isolated events, as explained in the prior framework. Now, in this chapter, we discuss evidence that music uses isochrony to achieve social bonding with coupling of motor systems via entrainment. Crucially, we claim that for speech rates to be effective in prosody, it needs to be dynamically changing within that range, not to retain predictable intervals for entrainment. So it's a bit like saying there's no goal for isochrony in speech. The speech rate needs to change in order to be effective. It's a bit like saying if we can use periodicity, if we can use our sensitivity to pitch as effective in communication, it needs to change to convey effective communicative goals. If it's the same exact period, it has no effect, right? So there's a range within which these things need to change. And the point here is that in music, it needs to be steady. In speech, it needs to change. And I think a lot of the research on speech rhythm kind of went astray because of the representation of rhythm in music is so strong in our way of thinking. All right, so to that end, going back to Proper, we are nowadays experimenting with methods to represent speech rate as a moving target using trajectories instead of a global measurement over a large portion of speech. Because often when we say speech rate, people are talking about a global measurement. And we are talking here about a trajectory, something that constantly moves. And we're not the first to think about that, of course. But we think we can achieve this very effectively within the Proper toolbox. And what you see here is a first attempt where we have this dynamic speech rate trajectory depicted as the gray curve overlaid at the bottom of the plot. I can play the speech example here.
Auch eine Bachblütenkur kann nur Dr. Barber machen.
And again.
Auch eine Bachblütenkur kann nur Dr. Barber machen.
Right, so you can see here, when this goes up, it's measuring distances between landmarks. When this goes up, those distances are shorter, so it's faster. And when this goes down, those distances are longer. And the reason why it's up for fast and down for slow is exactly because we want to think of it as the, let's say, the evil twin of the F0 contour just above it in the next, the other temporal regime. Okay, so the take-home message of all of this is that Priors provides a simple and effective framework for modeling perception-based aspects of speech in linguistic terms. The Proper toolbox provides evidence that we can effectively account for phonological phenomena with continuous primitives, and sometimes we should listen to the voices in our heads. That's it.
Okay, thank you so much for this great presentation, Aviad. And now it's time for questions from the YouTube platform. We'll be waiting a few minutes because people take some time to write down their questions. Thank you. Meanwhile,
Thank you for your presentation, Aviad.
Thank you.
Meanwhile, I'd like to one day to compare this periodic energy to other possible traces, like the traces that Fred Cummins used in the beginning of, at the end of the 90s, which was called the beat wave, with the quantity of energy throughout the utterance in a very specific band. Around F1 and F2, which closely related to the Picenter phenomenon, where I think you know that in the 70s, then explaining how we perceive syllables by trying to tracking CV transitions. I found that your algorithm for using to detect syllables, phonological syllables I saw, it's very close to the algorithm that you can use by considering the CV transition, the rate, velocity, speed from low to high energy using these beat waves. The difference is that they detect what is called V2V units, the beginning of the between two vowel onsets. But I think there are several close connections between these two ways of detecting at least phonetic syllables, because I think that you could have problems in cases of you perceive a phonological SIB, but the signal is very weak. I don't know if your method will still work for detecting phonological syllables when the speech signals for particularly reduced syllables is very weak. I don't know if you try that, but sorry, I will talk about that later. You have the first question from the platform.
But I have okay. But I like what you said. I think it's. I'll just want to comment quickly on that. This is on our to-do list right now to add the peak velocities of our intervals, and to then also look at the resulting derivative peaks to try and see whether we can see the boundaries strength like that. And maybe then, if we can include the boundary strength in our formulas, we can deal with the fact that indeed some in real speech many times these idealized demarcations do not appear, and things are coalesced and broken down. So yeah, it's not so clear as.
Yeah. Okay, thank you. If you, I don't know if we can read on the chat box. You have your first question on Jian Fenggu.
So right now I'm still struggling with
okay.
that.
Samuel, could you read it for him?
Sure. So this is our first question from YouTube, from our audience, and this is from, and I'm sorry, I'll probably butcher their name, but this is from Jiang Fengguo. They ask, they congratulate you for your presentation, and they say, you said that synchrony is nearly as good as F0 peaks for checking pitch trends. Then why should we use synchrony instead of tonal alignment, and why shouldn't we?
Okay, that's a great question. I think I heard the whole thing, right? So, what I showed, it's a good question, because what I showed is actually when we compare tonal alignment and synchrony, I was happy to show you, yeah, we get similar results. We can do the same type of job. It's not like we did a better job, but bear in mind, we compared in both of these cases. That was both the study from Russisch, Winter, and Mücke, and also the works from Kangemi's dissertation. We compared material that was prepared within the lab to have those very nice contours that we expect. And when we have those nice contours that we expect to find, then there's no reason why tonal alignment will not do a good job for us. I have other problems with this notion of tonal alignment, because then it gives a lot of power to these turning points, which I think is problematic in other aspects. But as a way of working with the signal to detect whether you can characterize something happening or not, tonal alignment is fine. The problem is if you start to look at different types of speech, not the ones that you create in the lab, you will often not find speech that is not long stretches of sonorant. So you will have a lot of discontinuities in your F0. And you might not have those nice F0 turning points that you need in order to make those different measurements. And then even if you do, you usually measure them with respect to one privileged position in the structure. So the advantages for us is that we can do the same when we have the same material. But what we can do with synchrony, which I think is a great advantage, is we can study all of the syllables in any given structure, or at least we can characterize them reliably for those aspects of the F0 contour. That's the point.
Yeah. Other questions?
It seems to be the only one until now.
Okay. I would like also to thank you for this nice script. Nice. I would like to test it with compare with the way I do similar stuff. But I changed the subject. I saw on the list of possible markers for focus from the study by Samuel Rosich, I think. I don't know. And there are some articulatory possible predictors. I think tongue peak velocity. They are actually use articulatory gestures. I understood.
Yeah.
And have
Yeah,
they tried to look at the jaw movement instead of the tongue movement? Do you know that if they try to use the jaw movement?
I do not know. I don't think they would have taken it out from this list.
Yeah, probably not.
But there's another list, right? So this is for
Yeah.
the two different types of comparison. The other one is here. But
Yeah, vertical tongue movement, tongue position, but not jaw. Okay, it was just you have a second question for you, Aviad. Could you read it, please, Samuel?
So this is from Simon Verle. I don't know how to pronounce their surname. They thank you for your presentation. Okay. This seems to be a Germanic surname. So, but anyway, they wonder. They say, as I understand it, the proper metrics mostly measure things that happen in the space of one syllable or between two adjacent syllables. Is there currently something in the toolbox that can account for more holistic or utterance level phenomena?
No, it doesn't mean that. So so first of all, yeah, nothing like that exists out of the box, but that box is open. So if somebody has an idea of using some of the elements here, and that would especially mean the periodic energy curve that we can produce with this workflow, they can take it and then apply it with some other things that we didn't think about, and that I definitely encourage people to do that. But there's also something that we're working on nowadays with another colleague here, Konstantin Kaland, who has this. He's working on contour clustering. He has this tool where he's looking at F0 contours and directly compares them via contour clusters, via clustering. And so we're trying to do that not with a continuous F0 contour, but with a list of proper metrics. So we're throwing lots of F0 contours that are characterized by a sequence of proper metrics. And we want to see if that's useful in, again, with you, when you do exploratory research and you have a bunch of stuff and you want to see if anything can be divided into categories and stuff like that. So that's something that we're working on, and that I think you could kind of use the syllable internal metrics to infer something about a larger pattern.
May I comment on something related to that? I think that it's related to your last slide. I think when you have data of several utterances in a sequence, and you use and you be able to use clustering techniques, you can use the peaks for detecting different levels of a hierarchy of rhythmicity, and one of these levels will certainly be the utterance level one, because I have applied that using only in syllable size duration to my data on Brazilian Portuguese, and I found 3 or 4 levels of hierarchy, and one of these, the higher one, was the utterance level one, and the algorithm was able to detect utterance boundaries based on this hierarchy of duration-related data.
Was it around 1 hertz, this slower?
Yes, it's around between 1 and 2 seconds, I think. It's 1 and 0.5 hertz, as you said at the beginning, because it's very close to the order of magnitude, as I probably know, of the reading in poetry. You know that when you read Alexander, 12-syllable poetry or 10-syllable poetry is around 2 seconds. It's the limit. Probably the limit of our capacity of retaining information about the verse, the line, I think.
Right, 2 seconds pops again and again is that boundary, but probably it's even before we reach 2 seconds. It's already when we're not good at integrating things. That has to show something about memory limitations.
Yeah.
And there's really good work now on by Maya Inbar and her colleagues on 1 hertz brain oscillations being very nicely related to the ability to chunk intonation units. So the idea that unit tend to, much like syllables, tend to have a central distribution around 200 hertz. It seems like intonation units have that 1 hertz tendency, and then that again kind of plays nicely with the idea that when you get closer to 2 hertz, we lose something important with our abilities to integrate information.
Yes, sure. I think it corresponds to about between 1 and 2 seconds, about 1 and 0.5 second, and it's about 6 to 7 syllables. This unit, which correspond to the famous 7 plus minus 2 magic number. I think.
Although it was updated to 4 plus minus 1 at some point. It's even. Or maybe we started remembering less.
Okay. Okay. Thank you. Any other questions, Samuel?
No, I don't think so.
Just a comment. I first saw this trace with different degrees of thickness in a presentation by Francesco Giangemi in Speech Prosody in Lisbon, I think. It's a great idea. And the idea of combining duration intensity using the mass, your model is great as well.
Thank you so much.
But I think you could, I don't know if you compare with a binary perception of focus, people saying if it's focused or not, or if you compare it to a gradient information about focus by asking several people if the same question binarily, but after that computing the proportion of listeners that responded to this question. The higher the proportion, the higher the strength of this focus thing. And maybe if you relate production data by using regression to this more finely grained perception information, you could probably better analyze the different possible candidates for predicting focus, and probably this hierarchy that you showed to us could change by using more finely grained information and prominence. What do you think about that?
I think it's a great idea, and we are actually doing something similar now. So can I ask you a question? Example that I was playing is one of something like 250 extracts we have from the TV News Archive, where people use this expression, and this expression is pragmatically very interesting because it's the same lexical string, but it has different pragmatic functions. It's usually not a polite way of asking a question, but it is also that. And so and of course, it invites you to put some highlighting on different elements. So, for example, can I ask you a question, etc., etc.
Yeah,
So
yeah.
we definitely plan what you mentioned. We don't have access to the articulated data in this case, but everything as you mentioned, I think, is pretty much what we plan to do. So we plan to give this to many participants that will be able to tell us to what extent different elements feel prominent to them, among other things that we want to check. And then we want to compare that with the results that we get bottom up from these types of metrics. And hopefully we will see some connections in the ballpark of what you were mentioning.
Okay, thank you so much. And any other questions, Samuel, from YouTube platform?
No.
No? It's 1 minute to 2 p.m. here, then it's about time. And once again, thank you so much, Aviad, for this great presentation.
Thank you.
And it was great for me to see all this. Thank you so much.
Me
Have
too,
a
thank
wonderful
you.
afternoon. Okay, bye.
Bye-bye.
And thank you, Samuel, for your work as well. Thank you.
You're welcome.
I will stop the transmission. Tá me ouvindo, Bruno Samuel?
Então,